Hello people, buckle up for today's video, which is going to be, as you can see, about curve functions and efficiency. So efficiency of an unbiased estimator. So what we're going to do today is prove a simple yet very important, let's say, theorem that characterize curve functions and efficient estimators. In more details, so in depth, what we're trying to say is, let's assume that we need, so without going too much into detail, under suitable and not too much strict regularity assumption, there exists an unbiased and efficient, meaning, i.e., sorry, I can't write today, that its variance, we're going to call it Tn as usual, its variance is equal to 1 over the information matrix, Fisher information matrix, whatever, depending on whatever it is. It will be an Hessian matrix if it's not scalar but a vector. Hence, this is basically meaning it reaches the Rao-Kramer limit, right? So it is efficient if and only if. So we're characterizing this curve function, which is defined as the derivative with respect to obviously the parameter of the this is defined, let me just say it, this is the log likelihood, so the log of the likelihood function. So if and only if, you can write this curve function as what? Basically as a multiple of the information, the Fisher information. Now, so this is before we prove it. So I'm gonna write proof either way. But before we prove it, I want to say why this result is pretty important, and that is for a what you could call a corollary, and that corollary basically kind of finds a relationship between efficiency, so efficient estimators, and MLE. So obviously this stands for maximum likelihood estimator. So this theorem provides kind of a lemma in the way. And if you want to see this as a theorem and the other as a corollary, okay, sorry, I'm talking about nonsense. That's not important. But this provides a very simple proof to the fact that you can basically find a relationship between efficient estimators and maximum likelihood. Now, that being said, which as usual, I always think it's pretty interesting to see why we do certain things in our, I mean, this is not a course, but why we do it in mathematics. So, without further ado, if we, for simplicity, we defined U as Tn, our estimator, right, unbiased and efficient estimator, and V as the curve function. Remember, this is a function of theta, right? So at this point, we can recall, let's make a recall, that the covariance square of u and v is, where u and v are random variables, is less or equal than, as usual, write theta here to remind us ourselves that we are in under parameter uncertainty. Okay, right. Now, where does this come from? Well, this is nothing but Cauchy-Schwarz. God, can I write it? Schwarz, maybe. I'm pretty sure it's misspelled. So, it's very simple to see that if we remind ourselves, or once again, of this is the correlation coefficient, which is defined as the covariance over what? Over the product of the standard deviations. Now, if we take a square, we can then write this as the product of the variances, right? And from this, this is defined between 0 and 1. From this, it's also very simple to see that this inequality holds. When does the equality hold? Well, very simple. When this is 1 and they are linearly, there's a linear relationship, they are linearly correlated, I guess you could say, then at this point, so if there exists a linear, I need to learn how to write, relationship, then the equality, and let's write it for extent. So covariance square of u and v is equal to the product of the variances, u and v, right? Holds. Perfect. Now, if from now on it's all basically computations, so we're gonna just go pretty quick on it. Now, so what have we written? We've written that basically we're saying, okay, this equality holds if and only if they are linearly dependent. Hence, we can write the score function as like this, right? For C1, C2 constants, right? At this point, we take the expectation. So let's write like this. So the expectation of this boy, this guy right here, what is it? Well, it is going to be the expectation. So I'm just going to do it. Just going to write it. It's this thing here. Obviously, the expectation is linear. Linearity of the expectation. Okay. Tn is unbiased. Right? That's what I like to do. I like to write the reason why I'm doing some things on the equal sign. Perfect. So this comes down to C1 plus C2 theta, right? And this is actually 0 because the expectation of a score function is 0. So what have we found here? So we found that, that's right here, C1 is equal to minus C2 theta, okay? But at this point, we can write this relationship here, this equality. Oops, nope. can write this. Perfect. Okay, so is equal. So C1 is equal minus C2 theta. So this is C2 times Tn minus our parameter, right? Okay, now what do? We multiply by the square function. I don't know why I said square. Square function, right? So we get this square is equal to what? To C2 square function minus C2 theta square function. Sorry, I'm missing a Tn here. Theta square function. Am I right? Yes. Perfect. Now, once again, we take the expectation. So I'm going to use the power of technology here. Perfect. Oh, by the way, people, if you find any mistakes or if you have any questions, any remarks you want to make, obviously that's what the comments are for. Mistakes, I mean, it would be my goal not to have many, but to make many, but we're human after all. And if you want this file as PDF, please let me know also down in the comments so I can start doing it. I can leave you the PDF version. Awesome. So perfect. So what have we got here? So this is C2, the expectation of the square function, the square function minus C2 theta, the expectation of the square function. Perfect. So this expectation is actually equal to 1, and that is because we can write this as so obviously we're going to write it as integral of what? Of Tn of x, the derivative. So the square function, we keep on writing it this way, right? Smaller x times what? Times, we can write, as we are in the random sample, so the classical setting, the usual setting. So this is random sample, this is equal, it's nothing but all the product of the PDFs, but it is a random sample, so they are IID, right? So this, we can write it this way, right? However, from the fact that Tn is unbiased, Tn is unbiased, right? So we can write this chain of equalities, right? And this is equal to let's forget about theta for a moment, right? This is an x. Okay, awesome. So it doesn't matter. This would be obviously Rn. This would be x. Okay. So from this we can, and here's why we need some suitable regularity assumption. We derive respect to theta. So we get 1 is equal to Tn of x, the derivative theta x of x. Now it actually makes sense to write this. Okay, but as we said, this is actually equal to what? To the derivative of the likelihood function, right? And this would be, we can write this as the likelihood times, and this is nothing but just rewriting things. Right? This is really, so I mean, this would be finally just to conclude derivative obviously of the log likelihood. Why? Well, so okay, this is nothing but the chain rule. As a matter of fact, if we write here the derivative of the log of something is equal to what? To 1 over something times the derivative of something, right? My math teacher in high school used to say the derivative of the log of my grandma is equal to 1 over my grandma times the derivative of my grandma, right? So, sorry, yes. So at this point, this is equal to this times the log likelihood, right? This is equal to the derivative of log likelihood times log likelihood. Perfect. So hence the equality. So basically we've written that this is equal to this piece right here, which is right, as you can see, where, as I was saying, as you can see here, we've got exactly what we had written, and sorry, it took me a while, but at least you know why this is equal to 1. So what we've written is the expectation of the square of a log likelihood is equal to C2, and this also is equal to 0. This is a property of a well-known property of this square function, which I will not prove. It's literally, you just need to use the definition. So it is equal to C2, but this is by definition the Fisher information, right? So C2 is Fisher information. At this point, what we've written is the, so we found, remember, the square function is equal to C2, I mean, it was equal to C2 minus, right? This is the Fisher information, hence the claim. Now, sorry if it took me a while to prove this, but I think that I could have told you was equal to 1, and I left it as an exercise. But I think it was more, let's say, complete to actually show you why. And I mean, it might not have been obvious, but hopefully I tried my best. So as again, any questions, let me know down in the comments. Any mistakes you see, please let me know. There shouldn't be any. And yeah, thank you for watching, and I will see you in the next one.